homework.
So,
Sorry, Paul?
so it's relating to Avogadro,
Yeah.
because you asked last time, what did Avogadro did?
How did he actually work it out? Yeah.
He didn't. The thing was named
After him.
after him. All he did was, it says, two volumes, or two gases, at the same pressure, contain the same amount of stuff.
Yeah.
The volume is the same, because, well, he said he...
How did they work? How did they work it out?
How did he work it out?
Avogadro number.
Thermodynamics and pressure, as in nRT.
PV equals nRT.
PV is in nRT. Yeah, reading is all those. It's complicated how they came up with it, but basically it's the amount of gas.
But it's just named after Avogadro.
But it's just named after Avogadro because Avogadro said that a volume of a gas, two different volumes of a gas, have the same volume, or two different gases
at the same temperature and pressure have the same number of atoms.
The same are the same volume.
Yeah.
Which means, yeah.
I never really understand why that's true.
It's a lot of maths and a lot of kinetics and a lot of.
Yeah, it's a fact that I know, but it's the question is why, and that I don't really know.
It's complicated because it's got partial pressure, isn't it?
Yeah. We'll gloss over some of that.
So yes, that's.
Yeah. Well, I do need to work out what the height is, whether it's 1500 metres or miles or whatever.
I think that's English chemistry. I thought it was just a kilometre, but.
1500 kilometers. There's my fact.
Yeah.
How long have I got?
6 minutes.
Right, I'll go 7 actually. Yeah. I'll run some route. Your timing's not quite right, is it? With real time, what time was that?
Well, I tried, but after I type all the stuff out once I,
Yeah. So. alright to do this for a sec?
Yeah.
Okay.
If you could look at the camera briefly. Okay.
Yep. I still have time to do that, okay.
Done.
Ready?
We're in
42.
40 seconds, apparently.
Welcome to GCSE Chemistry. We're live and we're going to have a look today at nano size things, nanoparticles, and then get a little bit smaller and we're going to look at the size of atoms and these lovely things called moles, the amount of substance. So let's start off with size and looking at nanoparticles. Let's have a look. A nanoparticle, well, what is it? Well, it's things we're going to measure in nanometers, and I can say that 1 nanometer is really small. Take your pick how you're going to spell this one. And 1 nanometer is going to be about 1 times 10 to the -9 meters. So this makes it about 1/1000th of a meter in size. And if we start having a look at the scale of some atoms, and let's sort of look down about the size of perhaps, let's say, 1/10th of a nanometer, then this is the sort of size that we're going to find an atom is. And when we start about talking about nanoparticles, they range in size from about 1 to 100 nanometers in size. And so particles this size are called nanoparticles. Well, they're really quite small, and we need to know a little bit about them because materials behave very differently when they are really small, sizes under 100 nanometers. The surface area to volume ratio here is very different to real world size things, and we meet some interesting nanoparticles. One of the ones that we see, glass. We can have glass nanoparticles, which we could take some glass beads and we could coat them with various things. The cosmetic industry is well known for its work with nanoparticles, the face creams that you try and use so that they go deep inside the skin, sunscreens, deodorants, things like that. We've also met some interesting ones with silver. Silver is fairly toxic to bacteria, and many of us see these silver socks that we can get with some silver put into the sock, because nanoparticles of silver will in fact kill off bacteria, and it gives you socks that don't smell. Let's go and have a look at some nanoparticles and what they really look like. And I've got some models here that might give you an idea. One of these things that I want to look at is this one. This is just a model of a piece of graphite, and graphite, if I turn it to the camera here, you can see it consists of some flat sheets joined by very weak bonds, and these wiggle all over the place. And this means that we can actually slice off a piece of basically graphite, make it really small, and this slice of graphite, if I slice it off, we call graphene. So let's do that. And there I've got my sheet of graphene. What can I do with this? Well, one of the clever things that we can do with this is we can roll it up. And if I can roll it up and I can join it together, then what I've made is a nanoparticle size tube called a nanotube. So this is here a carbon nanotube, and in fact in reality it would be very much longer than this. I don't want it much longer than that because I've got a problem trying to store it if it's any larger. But we've got this particular tube that maybe we could either put things in, or because these tubes are very long, they're very light, but they're incredibly strong, because this is just carbon molecules just joined together, then this becomes known as carbon fibre, and it is stronger than steel, lighter than steel, and used in things like tennis rackets and all sorts of other things. Carbon fibre you meet, but it's the actual molecules at this scale that make these tubes that give it its strength. If we can take that and we can roll it up instead of a tube into a ball, then we've made a different type of particle. Both of these will conduct electricity because they've got these only 3 bonds being used, and we've got an extra one, so there are, if you like, clouds of electrons, free electrons. We'll call them delocalized electrons moving around, so they will conduct electricity well. And this, well, if we could put a drug inside here, we could perhaps deliver this specifically. So these are called Buckminster fullerenes for short, discovered, made originally by a gentleman called Buckminster Fuller, and these things have great potential to do all sorts of things, but at the moment they're still at the design stage. So carbon nanotubes, buckyballs, useful because their nanostructures enable all sorts of things to be done. And if you're interested in nanoparticles, then there's a lot of research being done on this at the moment, and I managed to watch online a nice little race between several different nano designed cars, nanoparticle cars with wheels that rotate. Very clever what we can do with molecules nowadays, and it's only going to get better in the future. So quite interesting. But there are problems with some of these nanoparticles. I said that things are different when they're small. So are there any extra risks when they're small? And the answer is possibly. And this we need to investigate. Okay, next bit. We're going to look at something interesting. And people find this really interesting. No, I lie, they find it really difficult. The concept of moles. And they really don't like things like moles. It's sort of something that's not nice. But in fact, a mole isn't that difficult. Not really. A mole is simply the amount of substance. And the amount of substance is just a measure of something. We use meters quite happily, and people are happy with meters, so why shouldn't they be happy with moles? Your mum might ask you, go and get me a kilogram of sugar, 2 kilograms of flour. But it would have been better if someone had said to you, go and get me a mole of this, a mole of that, and then perhaps you'd understand it a bit better. Right. So let's move away from the nanoparticles and let's have a look at moles. So let's take a simple reaction, and let's take something like a gas like hydrogen, and let's react that with another gas, chlorine, and let's see what happens. And what we do is we make HCl. But this reaction isn't balanced, and so before we do anything we need to balance this reaction. So if I've got 2 hydrogens at the start, I must have 2 hydrogens at the end. If I've got 2 chlorines at the start, I must have 2 chlorines at the end. We can't change the formula by putting in extra numbers. I simply put a large number at the front to say that I've got 1 molecule of hydrogen reacts with 1 molecule of chlorine gas to give me 2 molecules of hydrogen chloride. So this is now a balanced reaction. Let's think about that one. If I've got this, then these things are always going to react in this proportion. Okay, let's now go off and have a look at something else you're familiar with, and that is the periodic table. And here I've just got a cutout of a bit of a periodic table. And let's have a look at a simple substance. And I'm going to look at lithium fluoride. Lithium, then 7,3. So lithium 7,3, and that I'm going to react with some fluorine, which is 19,9. What do these numbers mean? Well, we know that the 2 numbers, the number 9 represents here the atomic number. And we know our atomic number is the number of protons, or it can be the number of electrons. And in this case, that's 9. The other one, we call it the relative atomic mass. And that is the number of protons plus the number of neutrons, which equals, in this case, 19. How do we get these things? Well, when scientists started out, they looked at trying to weigh one atom on a scale. And they noticed there's a little problem. Trying to weigh one atom on a scale is just impossible. What they could do, however, is they could compare the masses. And the first obvious one was to compare hydrogen, because it's the lightest, with everything else. But there's a problem with hydrogen, isn't there? And the problem with hydrogen, it's a gas, and it's not going to make life really easy. Another option would be to use oxygen, but again, oxygen's got a problem. It's a gas, it's not going to be very easy to do, and there are various other problems with it. So we've got problems with hydrogen and with oxygen, in that they have these nasty things called isotopes. So after a while, scientists settled down and they decided on comparing everything with carbon. Now, carbon does have isotopes, so they were fairly specific, and we're going to look at carbon with 6 protons and 6 neutrons. Comparing it with that wasn't very helpful, so let's compare that with 1/12 of an atom of carbon, and that is going to give us the number 1. So now we can compare each element with that of carbon. Let's take a look at some carbon. And what I've got here is 1 mole of carbon, and that's 12 grams. So we've got carbon with its relative formula mass of 12, and I'm going to do is we're going to change the relative formula mass to grams. So we're going to have a definition that 1 mole of any substance is its relative atomic mass, or it could be its formula mass in grams compared with 1/12 of an atom of carbon 12. So an easy definition here, we've got our carbon and I've got here 12 grams. Let's look at this. If I hold it up to the camera here, you can see that I've just got a fairly small amount here of carbon. It gets a bit dirty, I'm afraid, because carbon by its nature is black and it sort of sticks to this pot. So I've got 1 mole of carbon, 12 grams. If I look at a different atom, and let's now choose a different one, and an easy one here to look at would be sulfur, And if we compare this with sulfur, so my sulfur here, 32 and 16. I'm not really interested in the 16 here. So 1 mole of sulfur will have 32 grams of sulfur equals 1 mole. 12 grams of carbon equals 1 mole. Let's look at 32 grams of sulfur. The first thing that we note when we have a look at these is basically we've got a larger amount of sulfur. I've got in there probably about 3 times as much sulfur. Well, let's have a look. Why have we got more sulfur? Well, that's fairly easy. If we compare the sulfur, which is here 32, which gives me 32 grams, compared with my carbon, which is 12 grams. If I were to look at an atom of carbon, it's got 6 protons plus 6 neutrons, and in my sulfur, if we look at the number there, 16, it's got here 16 protons plus 16 neutrons. So you'd expect each atom of sulfur to be heavier than each atom of carbon. What about size? Why does the sulfur seem to be much more than the carbon? Well, that's all to do with something else, which is density, and we find that does confuse people, that some things are basically heavier, if you like, their molecules, atoms are closer together, and that does sort of fool things a little bit. But we have got a decided difference here. This is 32 grams, much heavier than the carbon at 12 grams. But what they have in there is the same number of atoms. The same number of atoms here is something we call the Avogadro number. And the Avogadro number, Avogadro constant, is 6.02 times 10 to the 23 atoms. So, in 32 grams of sulfur, or in 12 grams of carbon, I have exactly the same number of atoms. So, 32 grams of sulfur has 6.02 times 10 to the 23 atoms of sulfur. 12 grams of carbon has exactly 6.02 times 10 to the 23, didn't write that properly, atoms of carbon. They've got exactly the same. And we're going to call that 1 mole. So 1 mole is 6.02 times 10 to the 23 atoms. 10 to the 23 is a big number. It is 6 times 10 with That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, going off the page, 23. That number of zeros. Wow, that's a big number. How big a number? So I took some of my students to a beach, and we arrived at the beach, and I said, well, let's imagine that 1 grain of sand equals an atom. So what does 10 to the 23 atoms look like? So we looked at the beach, and I got out my bucket and spade, because you would always take a bucket and spade to the beach, and I filled my bucket with my spade, filling it up with sand, and there's my bucket, and I said, is that 10 to the 23 grains of sand? And the resounding answer was, well, no. It's a bit bigger than that. It certainly is. So we looked at a excavator, these diggers, and it could dig up some sand, and its bucket, it could hold about 1 or 2 cubic meters of sand. Is that 10 to the 23 atoms? And many have thought, yeah, could properly be. But they were wrong. So let's look at the whole beach. And the whole beach goes down miles in either direction. 10 miles or so. Is that 10 to the 23 grains of sand? And the answer is no. So what is? Well, it's even bigger than most people imagine. If we take the United Kingdom and I cover this with a layer of sand to a depth of about 1,500 kilometres, then that equals about 10 to the 23 atoms, 10 to the 23 grains of sand. That's a really big number. If you go out at night and look at the stars, you can't see anything like that number. There aren't that number in our galaxy, and you can't see all of them by any stretch of the imagination. And if you look at other galaxies, you can look at an awful lot of galaxies in our universe before you get to 10 to the 23. 10 to the 23 then, an enormously large number. Right, so we've got our periodic table. The periodic table simply compares each mass of each different element with 1/12 of an atom of carbon-12. And in this periodic table, all the numbers have been rounded to whole numbers as best they can. There are a few that failed: copper at 63.5, chlorine at 35.5, a couple of examples of ones where they don't quite work. And this, my favourite interesting one of having tellurium and iodine, which seem to have their masses round the wrong way. So my periodic table does give us these masses, and we can use those masses to do some calculations. Let's go back to my first calculation, which was, we took some hydrogen gas plus some chlorine gas, and this gave me 2 molecules of hydrogen chloride. We can look up in my periodic table the mass of hydrogen. And the mass of hydrogen, it's 1. So this is going to be, I've got 2 atoms, so it's going to be 2 times 1. Chlorine is going to be 2 times 35.5. No, we're not going to get nice easy maths. And this is going to give me, to make HCl, 1 plus 35.5, which is going to give me 36.5, and there are going to be 2 of those. If we perform this sum, so 2 35s are 70 and 1 gives me here 71, plus I've got 2, that's going to give me 2 36.5s, which is going to give me 73. And what shouldn't be very surprising is the amount of stuff at the start must equal the amount of stuff at the end, because you can't do a simple reaction, expect things to sort of appear magically or disappear magically. Chemistry doesn't work like that. We add something, we remove something, we react something, and the volumes, the masses stay the same. Occasionally they don't, and that is usually an indication when you've got a gas given off. So let's take a different reaction and have a look at this. And what I'm going to do is I'm going to take a simple reaction of reacting sodium hydroxide and hydrochloric acid, HCl. Let's look at those. If we take this reaction, then I take hydrochloric acid plus sodium hydroxide, and this gives me, when it reacts, sodium chloride plus H2O, water. Now I chose this reaction because it's already balanced and it saves me an awful lot of effort. Let's see what this says. This says that 1 molecule of HCl reacts with 1 molecule of NaOH, and this will give me 1 molecule of sodium chloride plus 1 molecule of water. Now if I didn't take that, but if I took 6.02 times 10 to the 23 molecules of HCl, that will then react with, in the same proportion, 6.02 times 10 to the 23 molecules of sodium hydroxide. This will produce for me 6.02 times 10 to the 23 molecules of sodium chloride plus 6.02 times 10 to the 23 molecules of water. That's exhausting trying to write that out. This has got a better name. This we can call 1 mole. So 1 mole of HCl can react with 1 mole of sodium hydroxide to give me 1 mole of sodium chloride plus 1 mole of water. Let's do some calculations. hydrogen chloride, hydrogen's 1, chlorine down here 35.5, so that's going to be 1 plus 35.5, going to give me 36.5 grams. That's 1 mole. Sodium hydroxide, sodium has the number 23, plus oxygen, which is 16, plus hydrogen, which I hope you can remember, is 1. 23 and 16 and 1 gives us 40. So if I take 36.5 grams of hydrochloric acid and I take 40 grams of sodium hydroxide, both have the same number of atoms in each, and these react to give me some sodium chloride, 1 mole of that, which is going to be 23 for the sodium plus 35.5 for the chlorine. Add those up, that's going to give me 58.5 grams of sodium chloride plus H2O, which is 2 for the hydrogens plus 16 for the oxygen, and that's going to give me 18 grams of water. If we add those up, 40 and 36.5 gives me 76.5 grams, react to give me, oh look, 76.5 grams of the products. Whenever we do any reaction, this is basically what we get. Let's do a different reaction. This time I'm going to take another nasty substance and I'm going to react that with this. Right, this here is sulfur. It's got 4 oxygens joined to it, and attached to these oxygens here are 2 hydrogens. This group is the sulfate group, and when we add the 2 hydrogens we get not hydrogen sulfate, but we get sulfuric acid, H2SO4. The acid plus an alkali here, which is sodium hydroxide, is going to give me a salt, which is this time sodium sulfate. Now I happen to know the formula of sodium sulfate is Na2SO4 plus water. Before we can do anything with this reaction, we need to balance it. So let's go ahead and balance the reaction. I'm going to use a very simple method of trying to balance this reaction, and I call this CBA. Yeah, I can't be asked. We all know can't be asked. This is where we've got the chemical, the number before, and the number after. Let's see what we've got. Now, I'm lazy, and I can see that I've got SO4 here, and I've got SO4 there. It's not changed. So I'm going to take this as one chemical. So I'm going to have SO4 here. I've got some hydrogens. They are doing things, so we're going to count them up separately. And I've got a sodium, and I've got a spare oxygen. How many before? 2, 3 hydrogens, we said there was one sulfate, one Na, one O in the OH. Afterwards, then we've got two sodiums. I've only got one SO4. I've got two hydrogens, and I've got one oxygen. Well, if I've got two sodiums at the end, we had to have two sodiums at the beginning. And that means if I've got two of those, then I've also got an extra one of these oxygens, and I've got an extra one of these hydrogens. We've got sulfate, that looks alright. If I've got four hydrogens at the beginning, 1, 2, 3, 4, then I must have four hydrogens at the end. And the way of trying to achieve that is to put a 2 in front of there, because that also means I've got two oxygens. And now the sulfates match, the hydrogens match, the sodium matches, and the oxygen matches. So here I now have a balanced reaction. I'll do more on balancing reactions, balancing equations in another lesson. Let's see what we've got. H2SO4 plus 2 NaOH gives me Na2SO4 plus 2 waters. What do I know? I know that one molecule of sulfuric acid reacts here with two molecules of sodium hydroxide. One of those reacts with two of those to form one molecule of sodium sulfate. Let's just react this. So there is my sodium sulfate, and I've got two hydrogens left that can go on each of these oxygens to give me two molecules of water. If we know that's true, we know that 1 mole of sulfuric acid will react with 2 moles of sodium hydroxide to give me 1 mole of sodium sulfate plus 2 moles of water. And if we do our calculations here to work out what's going to happen, the hydrogen we know is 1, sulfur we know as 32, and we've got oxygen is 16. We know that sodium is 23. Let's do our calculations. So we've got 2 plus 32 plus 4 16s are 64, so that gives me 98 grams of H2SO4 react with, well, let's work out what 1 mole is. 1 mole of sodium is going to be 23 plus 16 plus 1, 40. So we've got 2 moles of that, so that's going to give us 80 grams of sodium hydroxide to give me Na2SO4, which is going to be 46, which is going to be my 2 sodiums. My sulfate here is 96, and we can add those up, and if you're not very good at adding those up, then you can always use a calculator, because you're always going to be allowed a calculator in the exam, which is going to give us 142 grams of sodium sulfate plus water. One water is 18 grams, so 2 18s are 36 grams. And if we add up this side and we add up that side, we won't be that surprised to discover that they add up to the same total. So let's look at these moles to finish. I've got a formula. N, the number of moles, equals the mass over the relative formula mass. N equals M over Mr. So the number of moles equals the mass that we're looking at over the relative formula mass. So let's have a look at a couple of simple examples of these. So if I want to work out then how much of magnesium I might have, so I've got some magnesium here. How many moles of this magnesium? Well, I happen to have weighed this. This is 24 grams. I now divide this by my mass. Oh, relative formula mass is 24. So here I have got 1 mole of magnesium. We can look at a whole variety of these different things. I've got here another interesting substance. This is 1 mole of calcium carbonate. If we look at calcium carbonate, CaCO3. Calcium, I can look up in my periodic table, weighs 40. My carbon weighs 12. And I've got oxygen, which is 16 times 3, 48, which gives us an overall total of 100 grams. So we know the relative formula mass of calcium carbonate. So if I have 20 grams of calcium carbonate, we know its relative formula mass is 100. So the number of moles that I'm going to have for this, and we will use the calculator, and the number of moles of this is going to be 20 over 100, and that's going to give me here 1/5, which you could have easily have worked out, and we can work out this is 0.2 moles of calcium carbonate. I've got some other ones. I've got a mole here of calcium oxide. Calcium 40, oxygen 16, 40 and 16 make 56. So 56 grams of calcium oxide equals 1 mole. Interestingly, to compare it with 100 grams of calcium carbonate, and they occupy here about the same volume. Perhaps the calcium oxide is actually slightly larger. Volume is nothing to go by. if I pick these two up, then these two, I can feel that this one is about twice as heavy. So volume doesn't give you much to go by, but what does give you something to go by is the mass. I've got more we could have a quick look at. I've got 1 mole of sodium chloride, and this is 58.5 grams of salt, sodium chloride. And look at the difference in that, double the mass. But this one, roughly the same mass, but the volume twice as large. When I started doing this and setting these out, I asked my wife if we could have some little containers to put things in, and she was very good. She went and got me some little containers, and it was good until I got my copper sulfate, and I tried to put 1 mole of copper sulfate in here and it wouldn't fit. So all I could get in here is half a mole of copper sulfate. Well, how much is that? Let's work it out. So if I look at my copper sulfate, I've got CuSO4. We can look in my periodic table, and copper comes in at 63.5. There we are, copper 63.5. The sulfur is 32. The oxygen is going to be 4/16, which is going to be 64. And so we can work out what the mass of 1 mole of copper sulfate is going to be, and this is going to be 63.5 plus the sulfur 32 plus the oxygen, 4 oxygens, 64, gives me a total mass here of 159.5. And so I put 159.5 grams of copper sulfate in my container, and it wouldn't fit. So let's take half a mole. Let's look at my equation. N equals M over MR. I want to work out the mass this time, so let's multiply both sides by MR. So the number of moles times the relative formula mass equals the mass that I want. My number of moles I want, we're going to go for 0.5, times that by 159.5 gives me the mass that we need. So I take my 0.5, multiply it by my answer, and we get 79.75 grams. And if I look at my copper sulfate, half a mole of that will contain 79.75 grams of copper sulfate. It wasn't the only one that I had problems with. I tried to get myself some sodium sulfate, and sodium sulfate, when I put it into this container, you can probably see slightly better on that, it fills up all the container with just half a mole of sodium sulfate. But it got worse when I went to try and get some magnesium carbonate. Just a quarter of a mole of that, which is only a modest now 21 grams, fitted in here. I could not get even half a mole in there, because as we said, volumes and masses don't seem to correspond with one another. So there's some sort of idea about moles. We can convert different numbers, different masses, if you like, to work out how many moles that is, and we can work out how many, if we've got so many moles, how much mass of this we've got. Let's do one more just to see what we can do. So let's take another substance to try and work out what it's going to be. Let's take nitric acid. Students don't like nitric acid, HNO3. So on our periodic table we can work out what the H is. H here equals 1. The nitrogen, I've got one of those. Nitrogen is 14. And the oxygen, we've got 16, and we're going to multiply that by 3. So we can work out its relative formula mass quite easily, and that we do by simply taking 14 plus 1 plus 3 lots of 16, which are 48, and that gives us 63 our mass of nitric acid. So let's suppose I have just 15 grams of nitric acid. How many moles is that? Then I'll divide that by my 63. The units will cancel, you see, and we'll just be left with the moles. So what we're going to have is I'm going to have 15 divided by my answer, which was 63, and that will give me 0.238 moles of nitric acid. You want one more? Okay. Let's suppose we've got so many moles of something. So let's have, I've got 0.1 moles of sodium chloride. How many grams is that? N equals M over MR. We're going to rearrange that to give me N times MR is going to give me the mass, and so we can work out what this is going to be. MR, we've already worked that one out. We know that sodium chloride is 58.5, so my number of moles, 0.1 times 58.5 grams, gives me here 5.85 grams of sodium chloride. So there's an introduction to moles, an idea about what they are, how they fit together, what amount of substance is. We'll look next time at trying to sort of work with these moles to balance some equations a bit better, to work out the yield of chemical reactions and work out some other things like atom economy and so on. So until next time, which will be at 11 o'clock on next Monday, if you liked it, subscribe, and I will see you same time next week. Goodbye. Thanks for watching.